Welcome to another video in the series about the C7000 compiler. This video introduces the restrict keyword, which is often used to make a wide variety of loops run much faster. My name is George Mock, and I'm your guide. Why is it important to know about the restrict keyword? Well, the C7000 depends on software pipelining of loops to achieve maximum performance. Something called a loop carry dependency is a common reason a loop may run slowly. And this video is about, well, what's that? How do you know it happened? And what do you do about it? And hint, the restrict keyword is somewhere related to all this stuff. This video uses one running example throughout, and I will introduce the source code to you. We've seen this before. I've used this in other videos, but it's not identical. I made a few changes, and we'll see what they are. But it's just, one function with one loop in it. That's what's important for right now. This is the command to build it. All of these build options have been discussed before, particularly in the video about compiler options, so nothing new here. The important one, source interlist, means, among other things, the assembly language file that is generated by the compiler is kept. So let's run this command. And notice this diagnostic. It's a piece of advice, performance advice, and it says consider adding the restrict qualifier to the declaration of out, and it's talking about this guy right here, to improve loop performance. Okay, so we will be talking about that in more detail. Now the next thing I'm going to do is, this is a very quick way to find out, well, what's the II of the loop. Now remember, the II is the key metric of a loop. I discussed that in the video about software pipeline feedback and what II is and how important that is. Trust me, for this loop that's only doing this much work, an II of 12 is embarrassing. It's just awful. This is terrible. Something's really wrong, and we need to understand what is happening. The compiler diagnostic said to apply restrict to the function parameter out. Well, what does that look like? Well, it looks like this. You write it between the asterisks and the name of the pointer variable. That's because you are modifying a property of the pointer and not whatever it points to. And what does it says? What does it say? You're telling the compiler that the memory locations accessed by out can only be accessed by out. Another way I like to think about it is that all the memory locations ever touched by out are owned by out, and no one else can touch them during the time that this is all happening. And in this case, it means during the time that the function weighted sum is running. Okay, this has to be true for every call to weighted sum. Okay, you can imagine there would be multiple calls to weighted sum with different pointers and different values for weights and stuff, and for every one of those calls, this property that you're telling the compiler must be true. If it's ever false, the code generated by the compiler may access memory in the wrong order, which is extremely hard to diagnose. You do not want to put yourself into this situation. You could spend a really long time debugging, working out that this is what happened. Okay. Now, this description of restrict that I'm giving here is a conservative definition. If you go research how it's described in the standards for ANSI C, ANSI C++, you'll see that it's a little more flexible. Okay. Well, the definition we're given here is never going to cause incorrect execution. It's never going to cause you any problems in that sense. The extra flexibility that you get by the definition into the standard, well, for one thing, it's harder to learn. This is fairly easy to understand and master. This is not so much. And the additional cases it allows are rarely seen in practice. It just doesn't matter very much that this has a bit more flexibility than the definition we're given here. So on balance, all things considered, use this definition. It's not going to cause any trouble. It's easy to learn. and it's easier to move forward with. To further explain what restrict means, I'm going to give two examples of when you cannot use it. And here's one. This is a call to the function weighted sum. And notice that we're passing the same pointer for those first three arguments. Remember, this one's out, that one's A, that one's B. Okay, both the input pointers and the output pointer are all the same. They're all pointing to the same, base address, whatever it is. You can't use restrict if you ever call weighted sum like this, okay? If you're somebody who supplies functions in a library, a collection of functions in a library, and you use restrict on some of the pointer parameters in those functions, your documentation has to indicate when restrict is used, okay? So that those who call your functions like this don't do this, okay? Here is the second example of when you cannot use restrict. This one doesn't use the weighted sum at all. It's a completely self-contained thing. You've got some function, aptly named bad example. It takes one pointer argument, and it has this expression in it. Okay, pointer, plus equals reference to a global array. And then here's a call to it. Bad example passes the base address of global array to this pointer. So for this particular call, global arrays being used here, global arrays being used here. It's being used in two places, therefore you cannot use the restrict keyword here, okay? Now at this point you're probably going, hey, these are not typical examples. Nobody actually does this. True enough, okay? Fair point. But that's not what I need you to think about. What I need you to think about is this valid C code? Does the standards for C and C++ allow you to write code that does this? And the answer is very clearly yes, it does. And therefore, by default, the compiler has to take the pessimistic assumption that this could be going on, and therefore, pointer and global array could be pointing into the same place, and it's got to generate code that takes that into account, okay? And as you've seen, that can cause your performance to be completely terrible, and the way you avoid the whole situation is by one thing, not actually doing these contrived examples, and in addition, use the restrict keyword to tell the compiler examples like this never occur in this program. Back to our example, let's try applying the compiler's advice. Edit the file. Remember, the restrict keyword goes between the asterisks and out. Save the file. And let's build it again. And let's see what the II is. Wow! Down to 2. What just happened? The rest of the video is about explaining what just happened. But I need you to be patient about it. There's several sort of small pieces of knowledge that we need to build up and then put them together to explain what happened. One small piece of knowledge you need is a basic understanding of instruction scheduling. And I will do that with this example here. It's pseudocode, similar to C7000 assembly. It's not the same, but it's close enough for this example. The order of these two instructions matches what occurs in the original C source code. And the question we need to consider right now, and this is just a theoretical exercise for the moment. Can you write these instructions in the other order? And if you do, will they compute the same result? Well, for this particular example, the answer is pretty obvious. No, you have to keep them in the same order, because if you put that move first, it's going to copy 0 to R4, and then you're storing R3 indirect of R4, which has got 0 in it, and you don't want to write to location 0. I mean, that's bad, and so on. So you can't change the order of these instructions, okay? But what if the second instruction uses a different register? Instead of R4, it picked R5, R7, any other register. Could they change order then? And the answer is yes. You could write these instructions in either order and you would still compute the same result in that case. Here's another instruction scheduling example. It's slightly more complicated. The last one was just registers interacting with each other. This one includes some memory references, okay? So none of the registers are the same. And again, I'd like to consider the question, can these instructions change order? And at first glance, you might go, sure, none of the registers are the same. These can go in either order, but what possible difference could it ever make? Well, consider the question, what if R2 and R8 are equal? What if they have the same address in them? In that case, they have to stay in this order to compute the same result, to get the same value in R4 and to start R6 to the same place. Okay? Back to our example. Let's edit. To remove the restrict keyword, put things back into the broken state. Oh no, but there's a reason for this. Don't worry, it's going to be fine. Okay, and now we're going to build it once more. Now our diagnostic comes out again. Let's demonstrate that the II is once again terrible. Yep, everything's back the way it was. But now I want to look at the assembly code, and I want to focus on something that I showed you in the video about the software pipeline feedback, the single scheduled iteration. Okay, so let's get a look at this whole thing briefly here. You may want to pause the video at this point, get a closer look at this, because I'm going to show it to you again with a focus on a few things. So in this example, these lines are copied from the single scheduled iteration we were just looking at, but I omitted the ones that aren't relevant to the discussion at hand. Okay, but I want you to notice how there's a load and a store, similar to the example that with the simpler example we were just looking at. Now within one iteration, there's no need to change the instruction order. You don't need to be worried about that. But what about this situation across iterations in the software pipeline loop? What am I talking about? Well, let's take a look at that. This is a conceptual view of the software pipeline in the ideal state, in the state where the II is 2 and everything's executing well, just the way we want it. This view is borrowed from the video about introduction to software pipelining. Some of the earlier slides gave this conceptual view of how our software pipeline is constructed, and this is similar to that. So if you find this confusing, the best thing to do is go watch that video. So time is proceeding here in that direction. This is a representation of the instructions for iteration n. This is a representation of the instructions for the next iteration, n+1. You know, you'll see the instructions are the same. If two blocks are adjacent like this, they are conceptually executing at the same time. Okay? So I'm only showing the load and store instructions. There are other, several other instructions that are in the software pipeline in a single scheduled iteration. This one and that one, I'm not showing them because I want the focus to be on these loads and stores. And there's a question we need to consider, and that's coming up next. And the question is, can these references occur in that order? The references I'm talking about are circled. Okay. This store to this memory location, this load from that memory location. In the original C source, this store occurs, the store from iteration n happens before the load from iteration n+1. But in this ideal software pipeline, they're occurring in a different order. Is that okay? Well, as we've already discussed in the previous examples, what about the situation where D0 and D1 have the same address in them? In that case, they cannot be in this order. So we have to, so for the compiler to generate this code, it has to somehow determine, somehow know that D0 and D1 can never point to the same address. Well, how can you do that? Back in the assembly code that's been generated by the compiler, we're looking at the single scheduled iteration. Okay. There are the load instructions I was focusing on. Here's the store instruction I was focusing on. And the question is, the store, this store from iteration n, can it occur after these loads from the next iteration, iteration n plus 1? And as we've discussed, if D0 could ever be the same as D1 is what I showed, but it's actually D1 and D2. If it could ever be the same as any of these registers, the answer is no. And remember, that's how we have things working in this particular assembly code right now, because the restrict keyword is not in place. So I want to show you another detail that's in the software pipeline feedback that talks about this. And that's this line right here, the loop carried dependency bound line. It says the number is 12. That is the minimum II the software pipeline loop has to be to satisfy this loop carried dependency. In this case, the loop carried dependency is between the store and the load I've been talking about. And this character here, called the circumflex, I've also heard it called a caret, that character marks the instructions that are in the loop carried dependency path. So let's go back to the single scheduled iteration and get a look at those instructions. All right, here they are. Sorry, I can't get the correct thing highlighted. These characters here, and here they are. Oops. Okay, so the load's part of the loop carried path, and then that leads into the multiplies, which leads into the add and the store. In this particular small loop, almost all the instructions are in the loop carried path, but it's really the path of the thing that's really driving it is this store and these two loads, the store from iteration n, and then these two loads from iteration n plus 1. Now that we know what a loop carried path is and how to break it, let's go ahead and do that. We want to edit the example, put in the restrict keyword where the compiler diagnostic said to put it. Save the file, rebuild here, and inspect the II. Yay, we've broken the loop carried path, and now the II is 2, which gives us the performance we deserve. While the compiler diagnostic said to apply restrict only to out, and that's really all that's absolutely needed to get the performance we deserve in this particular example, in practice, the restrict keyword is applied to all the pointer parameters to a function. And the reason is, it's just easier when similar things are handled the same way. It's just more consistent, makes your documentation more consistent. For instance, if you're somebody who supplies a library of functions, you can say something like, all of the pointer parameters are restrict modified, which means that you, as the customer calling these functions, have to ensure that all of the memory addresses for those pointers are independent, they don't overlap in any way, or something like that, and which is, you know, what the restrict keyword means to the compiler. And it just simplifies your world if you're using it consistently, even though for cases like this one, you only have to use it on the pointer being used to write through. I want to close this video with two references. The first one is to this long web address here. If you think that's too much to type in, that's fine. Just search the internet for C7000 compiler. I've tried that search with a few different search engines, and I always get this web address back as the first result. However you get there, you are at the home page for the C7000 compiler. Here's where you can download it, access the manuals, and more details like that. The second reference is to e2e.ti.com. This is for customer questions on any TI product, including the C7000 compiler. If your question is related to the compiler or a related tool, it will be answered by me. Thank you for watching this video in the series about the C7000 compiler.